in Paris last time at the RISC-V week 2022, I talked about reverse engineering a CV AISEC. I don't know if some of you remember this maybe. I'm back with a bit of more of an overview talk today, talking about trusted electronics. I'm in a hardware security session for a good reason, and I'll go for my next slide to talk about why. So when we talk about hardware security in RISC-V, there is a lot of different things that we already know and have in RISC-V, right? We have things like secure boot, we have trusted execution environments, we have countermeasures against side channels, we have memory protection, we have secure remote attestation, we have all these different solutions, and that's fantastic, and I absolutely love that. However, what we don't have so much and what we don't talk about so much is trusted electronics. What is it? Well, if you consider hardware security kind of on one end, that's maybe our basis. And if we go around that and go a little bit bigger, we get our trusted electronics, and finally that would be sort of the very big globe right around that would be the way to technological sovereignty. So it's kind of that tiny little bit more to hardware security, and I'd like to take just a couple of minutes to talk about trusted electronics. What does it actually mean? How does RISC-V work with it? What are some challenges we might have there, and where will we go in the future? So first things first, when we talk about trusted electronics, what does it actually mean for an electronic component? And the first thing some people might think of might be, well, it shouldn't have any hardware trojans, no backdoors, no hidden functionality in there, right? That would be something, a component I would probably trust. If I was aware that would be fine. The second thing would be that I would hope it would come from a trusted supply chain. Doesn't mean that that has to be a supply chain maybe in my own country or my own region, but that I can trust each single partner and each single transportation between those partners in our supply chain. The third thing would be that there should hopefully be some measures to protect against unauthorized changes. We don't want those in our designs or in our hardware or software. And finally, we have some minimized risk of unspecified behavior. And that's kind of maybe the answers you would get if someone said, well, what helps you trust a component? And we kind of went ahead and said we want to formalize or abstract that a little bit. We want to have 3 different requirements for trusted electronics that we can fulfill, and if they are fulfilled, we can say that is trusted. And we went ahead and kind of put those down. The first thing we have to have is that we must have a high level of quality and reliability, not only when you ship it, but also during the whole entire lifetime, right? So for my phone, that would be like 2 years, because I drop it every day. For a car, hopefully more like 20, 30 years. And if that's something we can guarantee, that's our first requirement. That's done. The second thing, and you've probably already figured out where this is going with RISC-V, is that the hardware must comply with a known and complete specification, and the functionality should not in any way deviate from that specification. Make sense? We want to have the specified functionality, nothing more, nothing less. And finally, the hardware must be sufficiently hardened against attacks. There should be some kind of mechanisms in there to ensure security and avoid vulnerabilities. Of course, the discussion here, what does sufficient mean? It's a good question, and I think some of the solutions we already have kind of go in that direction. But of course, I'm at the RISC-V Summit, so I want to talk about how RISC-V works with all these properties or requirements, whether we can actually fulfill them, and probably some of these are going to be very clear to you. I've kind of tried to differentiate a little bit between open source in general and RISC-V specific. So let's talk about the first one. We want to have a high quality and a good reliability. And of course, when we talk about open source, in our blue, we always have the topic of verifiability. We have many eyes. We have verification. We have by the community, and we have lots of different people looking at it. We had this case in software. I was talking to someone before about this supply chain attack we recently had on this encryption module, which was then found out that someone was pushing updates that were malicious over years. And it was found just before it kind of blew up. So that's obviously fantastic. That's an open source kind of thing, right? We have kind of the verification speed. We have shared tools that we can use. We have shared testing resources. We have community efforts, peer reviews, all these things. We get faster verification. Fantastic. We love all that. What is specific to RISC-V? We actually have, due to the way the ISA is set up, the ability to customize and minimize the ISA, which makes verification easier. We have reduced complexity, and that means that we have good reliability. And I think this is probably for this first point the most important part. Due to having this open ISA, what we've actually gained is a lot of new innovation, a lot of new products, which has led to more high-quality products. So the fact that this ISA is out there and it's open source and lots of people are working on it has actually meant that the output that we get is more reliable. And I think that really is maybe one of the most fantastic things about RISC-V from my point of view. Okay, seems pretty good. We have some challenges, of course. And this is the one that I've put on here that people might not like to hear so much. It always gets asked, right? Open source, is it mature enough? And of course, RISC-V, we know it's very mature. However, we've had discussions with companies who said if the chip is not on the website for sale and I can go click and add it to my basket, that's not mature enough for me. So whatever this might mean to you, it can be an issue. And if that means, well, I don't actually have test benches for my design yet, or if it means, well, maybe I don't have a good software ecosystem or support ecosystem, then that's something we need to work on. We have different implementation standards by different vendors, so we have maybe different uniformity, or we have varying uniformity in quality. And I've mentioned before, or just then, the availability of the software ecosystem. I think a lot of vendors here do have fantastic ecosystems that tend to be very specific, and I think especially on application level software, we don't have the ecosystem yet where we would like it to be for a mature product. The thing that comes with that is the ensuring of long-term support, and I think that's also where RISC-V is doing really, really fantastic work, but we're not there yet, would be my personal view of it. And when someone comes and says, hey, I'm working on hardware security, it seems like an odd thing to say, well, are you working on long-term support? But that is where we have to go if we want to go towards trusted electronics. So, seems doable. We'll get to the second requirement that we do have. We want to have the ability to verify that it complies to a complete and known standard. Some people might say, well, okay, we have other standards that are known. So, for example, specifications we have for other commercial things. We know the specification, yeah, but we can't ensure it's complete. I think that's the important part here. It's two different things. It's known and complete. And of course, open source means it is available for verification versus some kind of closed source design. Specifically to RISC-V, it's documented, and that's so important. I think one of the biggest issues we have with verification and formal verification is documentation. People tend to make their specifications kind of work for them, and then there's a lot of interpretability, what you can do with it and what it actually means. We have a very well-documented ISA with RISC-V, and that means we can actually precisely and really completely verify to our specification. We have a couple of companies here today. We have, I think, had a couple of talks about this, or we'll have, about the ability to formally verify RISC-V. I won't talk much more about it. It's fantastic that it's there. And finally, again, something RISC-V specific, which I think is fantastic and unique to the community, is that we actually have a foundation which governs and maintains specifications. So we can be sure that they really are understood and maintained in the same way. Of course, again, seems fantastic. We do have challenges. We have vendor-specific implementations. We have customization-specific extensions. Of course, for that, it becomes more difficult to really make sure that our component does comply to the specification. I think that's something that's very much fixable, though. Much worse, I would say, is the effort for formal verification. And I think if you look at some of the chips being made now, which may be already commercial, not all of them are formally verified, and not all of them are formally verified, for example, for security. So a lot of them will be functionally verified, but security properties will not be verified. And I think that's somewhere where we have to go if the component should be labeled as trusted. And finally, maybe personally, for me, coming from a reverse engineering point of view, biggest issue is that our electronic supply chain is not completely open source. And the verification of a physical chip, so of what we actually get back from our foundry, is very, very difficult. If we think of this picture, which I think everyone's probably seen from the 2020 Open Titan PR announcement, they were saying, in the past we've had it this way, that everything in red is open source, and there's this big gray block where we can't really look into it. And in the future, we're going to have, on the right, a lot more open source. Unfortunately, there's still this little bit of gray area where we do have a disconnect. And that makes it very difficult to make sure that the product that we do have at the end on our table does comply to specification. And I think that's an area where we're going to need more research in the future as well. Finally, we must have some kind of hardening against attacks. Again, community approach in the open source community is fantastic. We've got bug hunting, we've got many ICE principles. I'd like to go more into the RISC-V specific things, because what's actually happened with RISC-V is that it spawned a lot of research into specific hardware-based security features that we didn't have previously, just because we have the availability of this ISA where researchers can work with. Personally, for me, I said this 2 years ago, I say it again, my last 8 years of research would not have been possible without this kind of open ecosystem. So, and I think that a lot of the security researchers would say the same, that this really has been a driver. We do have security features, right? We've got cryptographic extensions, we've got memory protection, and so on. So these can really provide the building blocks for these secure systems, and that's fantastic. However, they do have to be put together in a way where it makes sense. And finally, we have, things like side channel and fault attack countermeasures out there. Seems pretty good. Third requirement, pretty much we can check it off. However, there are challenges, effort for hardening. We know nowadays that a lot of companies don't really want to do security because it costs more. It might be interesting, might be something fun to look at, but as soon as cost comes into play, we don't want to look at that. The product should work. We don't care if it's secure or not. So the effort for hardening really is an issue. Furthermore, the open sourceness can actually expose the architecture to potential exploitation. On the one hand, I might have vectors for attacks on end products, so I can easily see, okay, this product is using this kind of side channel countermeasure. I can then use this kind of attack to go against that. And maybe something I talked about 2 years ago, due to the open architecture, it becomes very, very easy for attacks on the supply chain because I have so much information about the architecture. So I can do things like hardware Trojan insertion or IP theft of maybe proprietary IP that is mixed in with a RISC-V core very, very, very easily. So this becomes much more likely to happen. I do have to say, long-term, the security will improve. We have to find solutions that are not based on obscurity, but rather really on secure cryptographic features. And I think with this open source ecosystem, that is the way to go in the future, right? I do have to do kind of this one marketing slide. What are we doing at Fraunhofer about this? And I would like to talk about 4 different initiatives or projects. I'll start with our V Elektronik. It's German for Vertrauenswürdige Elektronik. It's Trusted Electronics, so the short version V Elektronik, which was a platform project for 15 different projects in this topic. And what has come from that is actually a VDE, so German Society for Electronics, Fachgruppe, which will be a central point for all things trusted electronics in Germany. And maybe this is where I do the short marketing thing. If you're interested in joining a group like this, which will be doing research, but also training on these topics, feel free to contact us. And on the left-hand side, we have our 2 very big projects, which are very much focused on the areas of trusted electronics. The first one, Trusted Electronics Bayern Center, where we do things like secure elements based on RISC-V, but also attacking RISC-V chips in our state-of-the-art labs. And finally, the Bavarian Chip Design Center, where we really look into fostering more innovation in Bavaria, Germany, Europe, and so on, through chip design. So, I will come to the end of my talk, conclusion and outlook. For me, trusted electronics is the way to go to technological sovereignty. Hardware security solutions in RISC-V are a fantastic first start. However, we need much more innovation, and we need to bring it all together into a big picture to actually gain trusted electronics. And I think RISC-V and the open source ecosystem are a fantastic driver for this kind of thing, hopefully leading to some better solutions in the long term. Outlook, new regulation is coming. We know new standardization is coming, for example, the Cyber Resilience Act, which will make this kind of thing much more interesting. And I did ask a question in the beginning, are there a match made in heaven? I would like to answer yes, and I did bring a little animation because I like animations. And if there's questions, please, I don't know if we have time, I would be happy to answer some.
So thanks, Johanna. So I guess we have time for one question.
It is the last day, so maybe people are a little bit tired.
Oh, where?
Oh, there is one.
Just thinking about your second principle of conforming to a specification and wondering what that says about use of FPGAs in any of these projects, because clearly they can be updated later. So even if you're conforming to a specification at some point, someone could give you an update that means the hardware changes what specification. So have you thought about that aspect?
So from the work we've done now, it's been very much focused on ASICs. However, of course, if for FPGAs it remains the same, you would have to recheck that specification with every single update you get, yes. I mean, For FPGAs, it would
I was more thinking the advantage of the FPGA is you can conform to a new specification later, and I don't see how that would quite fit into your paradigm.
You mean you could go from an untrusted electronic to a trusted electronic?
Well, I'm thinking more of it comes out of the box trusted and it's conforming to a specification, but a future update could move it to, maybe a later version of the specification, and it's not clear to me that that's permitted under your rules.
If there is a verification that we are still complying to a non-complete specification, that would be perfectly fine. For us, the other thing that would be interesting is actually if the FPGA in manufacturing is secure itself, so that it was manufactured in the supply chain in a way that's trusted, so that the FPGA itself is actually complying to the specification of the FPGA, because we do know that there's things in an FPGA which are often not told to us by vendors. So I think that would be probably the more interesting question when it comes to FPGAs. But yes, if we update and we can still prove that it complies to the specification, that would be fine. It would still be labeled as trusted, yes. Does that answer your question?
Yes.
Yeah, I think so.
Perfect. Thanks so much.
So thank you, Johanna.
Thank
again.
you.